Welcome to Fluid Dynamics tutorials by Civil Thinking, and this is our first class on fluid dynamics. Now before I move on, I suggest you to please watch the video lectures on fluid dynamics one by one as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now coming to today's class. Now in this class we are going to see the application of Newton's second law in fluid dynamics. What we are going to do in this class is basically we are going to apply the Newton's second law on simple case of fluid dynamics, and then we will also solve a numerical problem on it, okay, so that we fully understand the application of Newton's second law in the fluid dynamics. Okay, now let us consider a fluid, okay, fluid mass. Now I am considering a small fluid element, okay, infinitely small fluid element, okay. It has a mass of delta m and it has a volume of delta v dash or del v dash, okay. Now let us say we have this path, and a fluid particle is moving on this path, okay. Now I denote this with S, this path I denote it with S, and why did I do that I will tell you in after a few minutes, okay. Now we have this fluid element, okay, and it is moving on this. Now according to the Newton's second law, the net force, the total force acting on any body, okay, is equal to mass of that body times the acceleration of that body, okay. So in the general way I can represent Newton's second law as summation of forces is mass m times the acceleration a, okay. Now in this case we have the mass of this element is delta m, okay, so I can write summation of force is delta m times acceleration, okay, acceleration. Now since this fluid particle is moving along this S line, right, let us say the acceleration along this path is as, so it is going to be as, okay. Now this summation of forces are the total force acting on a body, and in case of a fluid, on a fluid element, the forces can be the pressure force, the what we call that as the gravity force, that is the weight, or it can also be the the forces which are which is because of the viscosity, the viscous forces, okay. So the summation of forces, it can be due to, let me begin with gravity. Gravity force, okay, plus pressure force plus viscous force, okay. Now what are viscous forces? They are those forces which arise in a fluid because of the viscosity, okay. Now since it is our first class, okay, so we are going to neglect the the viscosity, we are going to neglect the viscous forces, and then the summation of forces are going to be only the sum of the gravity force and the pressure force, okay. Now since the particle is moving along this path S, okay, so we will consider the gravity force along S plus the pressure force also along S, okay. So in simple terms we are going to find all the gravity forces and the pressure forces only along the streamline, because in this class we are going to apply the Newton's second law of this fluid particle along the streamline, okay, this S, okay. By the way, this is called streamline, and I will tell you why it's called so, okay. Now mass, we know mass density rho is mass divided by volume, right. So from here I will get the mass to be density, mass density rho times volume, right? So I can write this delta m, because delta m is the mass of this fluid element. It is rho times what is the volume of this, it is delta v. Okay, delta v. Okay, so delta m is rho times delta v. Okay, now this acceleration, what is the value of this acceleration? Acceleration is rate of change of velocity, right? So acceleration is rate of change of velocity. Okay, so but before that I will tell more about this streamline first. Okay, let us first talk about streamline. Okay, now what is streamline? Streamline is basically any line such that when a fluid particle enters, let us say these are two positions, we denote it with s. Okay, let us say these are two positions. Okay, these are not particles, these are two positions on the streamline. Okay, now let us say the one fluid particle enters from this point. Okay, and it travels along this. Okay, it travels along this and reaches to this point. Okay, let us call this as point A and let us call this as point A dash. Now what is the property of streamline? Streamline is basically, if a fluid particle enters here, let us say it have a velocity of VA here and pressure of PA. Okay, then it will travel the path and it reaches A dash. Here the velocity is going to be VA dash and here the pressure is going to be PA dash. Okay, now one particle enters. Okay, and at this point, position A, it has a velocity of VA. Okay, now the property of streamline is, now if another particle enters, okay, then it reaches this point, position A, again the position of the velocity and the pressure of that the second particle is going to be the same, that is VA and PA. Okay, then if third fluid particle enters and it reaches the position A, again the velocity and pressure of that third particle is going to be same as those of the last two. Okay, that is VA and PA. So if at any time, okay, irrespective of the time, independent of the time, whatever and how many particles entered, okay, irrespective of the count, irrespective of the time, whenever a particle is here A, it will have the same velocity. Okay, then when they reach A, when the particle 1 reaches A, fluid element or fluid molecule or whatever, its velocity is VA dash and pressure is PA dash. Then when the second element, the second particle enters A dash, again it is velocity and pressure at position A dash is going to be same, VA dash and PA dash. Okay, but remember, VA dash is not equal to VA and PA dash is not equal to PA. What does it mean? It means there is variation in the pressure and the velocity along the path. Okay, so velocity and pressure, they are a function of what? They are function of path position. Okay, S. Okay, but velocity and pressure, okay, at a given time is constant. Okay, so whatever the time, irrespective of the time, fluid property, fluid parameters, velocity and pressure, okay, they are constant. Okay, at a given position irrespective of the time. So that is the property of a streamline. Okay, and we are going to see, we are going to apply the Newton's second law on this, along this streamline. Okay, now when when fluid property is same at all the time, okay, because at position A, for example, the velocity and pressure is always constant. That is, if we draw a curve, for example, for A, point A, if we draw velocity curve, it is always velocity curve, it is always the same, and if we draw a pressure curve, it is again the same. Okay, so this is called steady flow. Okay, steady flow. Now why do we consider steady flow and this all of these assumptions? So our assumptions are what? It is not viscous, okay, so viscous forces are 0, okay, this was assumption 1, okay. So and another assumption is the flow is steady, okay. So if I write the assumptions here, the first assumption is inviscid, okay, inviscid fluid or inviscid flow, right? What is it? It is where viscosity is 0, right? Second assumption is the flow is steady, right? The flow is steady, right? So these are the two assumptions. Now the question is, why did we make these assumptions at the first place? Because when you go, when you see a fluid in real life, for example, when you open a tap, for example, okay, when you open the knob of a tap, okay, for example, this is fluid pipe, and when you open it, okay, and you will see fluid coming, okay, but you won't see, it is not steady, okay, it is not steady, and there is the viscosity is not 0. But why did we consider this? We consider this so that we can understand the Newton's second law, okay. Now because as always in the science, in engineering, we always, what we do, we don't we don't deal with the real life, right? We don't basically consider the phenomena as the reality. We consider a simplified model of the reality, right? We consider the models, we consider the assumptions, okay, so that we can apply all these equations and we can apply, okay. So as we move on, we will reduce our assumptions and we will go, our models will consider the more reality, okay, right? Our models will be more close to the reality, okay. Now because we are understanding the fluid dynamics, okay, so the assumptions are always important, okay. Now we know a streamline, what a streamline is, okay, and we denote a streamline with S, okay. Now we will apply Newton's second law along the streamline, okay. We got the summation of forces is mass times acceleration, and what are summation of forces? They are sum of many forces, but we will not consider viscous, so we will consider gravity and we will consider pressure forces, but along the streamlines, and then we will add up and we will get some a new equation. By the way, we call that as equation of motion. Why equation of motion? Because the fluid particle is moving, and that will be the equation of motion, okay. So one by one, we will first find the gravity force along the streamline, then we will apply the pressure force along the streamline, and then we will add them up and we equate them to this, okay. So let us begin one by one. So gravity force, let us talk about gravity force, okay. Now again I am saying to you that my classes are always simple. I make things very simple so that you understand, okay, and I truly believe that you will understand everything, okay, because if you read a book you might get confused, things might be a lot complex, but right here the things are going to be a lot simple, okay. I will make you understand the complex topics in very simple way, okay, so that you will understand. So just bear with me, stay with me, enjoy my video lecture and understand the concepts, okay. So let us begin with the gravity forces, gravity force along streamline, okay, streamline. Now let us say this is our streamline, okay, S for streamline, okay. Now streamline, yes, one more thing, the property of a streamline is when you draw a tangent, okay, at any point, tangent at any point will give you the velocity, okay. So if you draw a tangent here, for example, if you draw a tangent here, it will give you velocity at A, okay. Now if you draw a tangent here, it will give you velocity at a dash. So wherever you draw a tangent on a streamline, that will give you the velocity at that point. Okay, that is the property of a streamline. Okay, now anyways, let us say we have a fluid element here. Okay, its weight is W. Okay, because it is small, infinitely small element, so we will call it as del W. Okay, because it is a small, so del W is the weight. Okay, so I will write here, this is our fluid particle. Okay, its weight is delta W or del W, whatever you call it. Okay, its density is, mass density is rho. Okay, mass density is rho. Now let us say it is inclined at an angle of theta with the horizontal. Okay, let us say this is the angle theta. Now let's consider, because we will consider a normal line. Okay, we'll write it as n, because when we have a streamline, okay, if this is a streamline, then there are other, we can find the other factors like the gravity force, the pressure force along the streamline, and also the normal to the streamline. Okay, but in this class we are going to see the things along the streamline, because we are applying Newton's second law on the along the streamline, right? But yes, I will do consider a little things which are normal, which are along n. Okay, which are normal to the streamline, but the whole of the class is going to be the Newton's second law along the streamline. Okay, now since this is theta, so this is also going to be theta. Okay, let me show it here. Let us say this is W. Okay, and this is our normal, right? This is our normal, this is horizontal line. Okay, so if this is theta, then this is also theta, right? So now when you want to find the components of W, okay, along the streamline and perpendicular to the streamline, okay, we will resolve the W along streamline and normal to streamline, that is along S and along N. Okay, so if I can draw, so this is going to be WN, okay, along normal, and this one is going to be WS, okay, along the streamline. Okay, so from this diagram you can clearly understand W normal is W times cosine of theta, right? Cosine of theta, and WS is W times sine of theta. But where is the motion is from left to right. Okay, motion is along this, right? Left to right, the motion is like this. Okay, so but you can see this WS, it is normal to the motion, right? Because it should be this component, so we will consider this. Okay, negative WS. Okay, this is going to be the component along the streamline. Okay, so our component is going to be negative. Okay, so negative of W sine theta is the the component of weight along, right? So from here we can write this is delta W normal along normal, and this is delta W along the streamline. Okay, so delta W along the streamline is what? It is minus W sine theta, right? Negative W sine theta. Now remember, not W, it is delta W, because weight is del W, right? Delta W. I hope this is very clear, and at any time if you have any doubts, first of all I believe you won't have any doubts, okay, because I will explain things in a very simple way, but still if It may be possible that you got some doubt, you didn't understand somewhere. You can comment or you can contact me. I will definitely help you. So now weight is what? Weight is, now first of all, mass density. Density is what? Density is mass per unit volume. Okay, let us say V dash is the volume. Okay, now weight, let me show it here. What is the value of weight? Weight is mg, right? Mass times acceleration due to gravity is weight. Okay, so delta W is delta m times g, right? So delta W is delta m times g, but mass is what? Mass is delta m is density times volume, right? So we can write mass as density times volume times g, right? But what is volume? No. Now what is rho times g? Rho times g is density times acceleration due to gravity, which is the unit weight, gamma. Okay, so delta W is what? It is going to be gamma V, right? Gamma times V, right? So from here, what is going to be the value of delta Ws? Delta Ws is going to be negative. Delta W is gamma delta A, gamma V dash, right? And then we have sine theta. Okay, what I did, I substituted the value of delta W here. Okay, and we got this. Okay, so I will copy it. Here we go. We got the gravity force. Okay, so we got this gravity force. Now we will find the pressure force along the streamline, right? And then we will sum them up and we will see what we get. Okay, remember, when we solve everything, we will get something, you know, very interesting and very important in fluid dynamics. Okay, so let us now begin the pressure force along streamline. Okay, pressure force along streamline. Okay, now again let us consider a streamline and let us consider a body. Now first of all, we have a normal, right? This is our normal to streamline. Okay, now let us consider a body here. In fact, I will consider a 3D body. Okay, now let us say along the stream that this dimension is delta S along the streamline. Now this is normal. Let us consider this as delta Y. Delta Y is the, you know, the dimension of this cubic fluid element perpendicular to the display, to the screen or to the paper page. And along the normal, this side is along the normal, it, let us say the dimension is delta, for example, n. Okay, now let me tell you one thing first. Let us consider a body. Let us consider a face. Okay, A is the length of this rectangle and B is the, you know, another dimension. A is the width and B is the length. Now let's say we have a force F on it. Okay, this force is perpendicular to this face AB. Okay, then what is the pressure? Pressure is force divided by area of this face. Okay, now what is the area of this face? It is A times B. Okay, A times B. Okay, so pressure is what? Force divided by A times B. Okay, or we can write F to be P times A times B. Okay, or force is P times area, right? Area. Okay, but this pressure is on what? Normal. It is perpendicular to the face. Okay, now when we see this, now you have multiple faces on this. Okay, you have multiple faces, right? But it is moving along this path. Okay, what does it mean? It means the net force is acting on this perpendicular face. Okay, the perpendicular face, which is like this face, but on that side. Okay, anyways, that doesn't matter. Let us say the force is delta F, this is delta Y, this is delta N. Okay, so delta F is what? Pressure. Let us say the pressure is delta P, pressure times area, right? Pressure times delta A is the area. Okay, now so I can write here, this delta F is pressure multiplied by area A, right? And this area is what? Delta N times delta Y, right? What is the area of this? This dimension multiplied by this dimension, right? Delta Y times delta N. Okay, so I can write delta P multiplied by delta Y times delta N. Okay, this is the pressure force. Okay, but what is the sign of this delta P? Okay, now again let me erase this. Let me show you here. Now let us say we have this fluid particle. Okay, it is moving from A to B. Okay, now if a particle is moving from A to B, it means pressure at A is greater than pressure at B. Okay, because when pressure is more on one side, it pushes a body into lower pressure. Okay, so the motion is from higher pressure to lower pressure. Okay, so for example, let us say the pressure here is delta P at this point. So to the left of it, the pressure is going to be for example, let us say the pressure here is P. So to the left, the pressure is going to be P minus delta P, P plus delta P. Okay, because a little bit more than P, because it is to the left. And to the right, the pressure is going to be P minus delta P, means a little less than P. Okay, so what is the net pressure? Net pressure is this pressure minus this pressure, right? So it is P minus delta P minus P plus delta P. It is going to give me the net pressure. Okay, so P and P will cancel out, so it is minus delta P minus delta P. Okay, so which is minus 2 times delta P. But since delta P is very small, okay, delta P is infinitely small. Okay, when something is infinitely small, so we can write 2 times delta P approximately as delta P. Okay, so this minus 2 times delta P is going to be negative delta P. Okay, so we have this negative pressure. Okay, so it is basically minus negative delta P. Okay, now so do we need any simplification? Let me see. Now you can see this, this the gravity force along the streamline, it is in terms of the volume, right? But here we have in terms of the area, right? So it will be better if we represent this also in terms of volume, so that we can have kind of uniformity. Okay, so that we can craft some beautiful equation. Okay, so in order to convert this area into volume, what I am going to do, I am going to multiply with what is the volume? Volume is delta N delta S, delta N times delta Y times delta S. Okay, so I will multiply with delta S and I will divide by delta S, that is the same thing. Okay, delta S will cancel out, so we have delta F is equal to minus negative delta P by delta S times, now what is this? This is the multiplication of three sides of a cube, right? And that is the volume, right? So it is delta V dash. Okay, so we got this equation. Okay, so this is our equation. Okay, so we also got this equation, okay, due to pressure. Okay, so we will sum them up, okay, somewhere. So let me copy this. Okay, now let us sum them up. So the summation is minus gamma volume sine theta minus delta P by delta S times delta volume, right, is equal to delta M times AS, streamwise acceleration, right? Acceleration along the streamline, right? Now we have this volume here, we have this volume here. Okay, now what if we convert this mass into some the volume thing, so that we can cancel the volumes? Okay, because the Newton's law is irrespective of the volume at any volume, so we don't need this volume element. Okay, so whether the volume is small or volume is big, the Newton's law apply on all of that. Okay, irrespective of the volume, magnitude of volume. So why to keep this volume here, right? So now because we have this fluid element, right, now it is volume is, this was delta S, this is delta delta Y, this is delta N. Okay, now volume is delta S times delta Y times delta N, mass is delta M, right? Now we know density is mass divided by volume, right? Volume. So from here we will get mass to be density times volume. Volume is delta V dash, right? So here I will write, instead of delta M, I will write density times volume. Okay, so again now we are able to cancel out the volumes, right? This volume, right, and volume will cancel out. Okay, so what we are left with? We are left with minus gamma sine theta minus delta P by delta S is equal to density times the acceleration. Okay, but acceleration along the streamline. Okay, so this equation we call it as equation of motion. Okay, so it is better if you just remember it. Okay, it is equation of motion. Okay, now but something I want to tell you something important about this acceleration. Okay, because we have to know what is this acceleration along streamline. Okay, because I told you the flow, if I show it here, assumptions, where did it go? Yes, this assumption. Okay, the flow is steady. It means what? Velocity is constant, right? Steady flow, in a steady flow velocity is constant at any time, right? Or we can say dv by dt, right, it is 0, right? But rate of change of velocity with respect to time, it is acceleration, right? It is acceleration. So acceleration is 0 in a steady flow. So the question is, how come we have this, right? Where does it come from? If the flow is steady, then why we have the acceleration, isn't it? It is a very natural question. If we are talking about a steady flow, then how come that we have this acceleration? Okay, so should we keep it as 0? No. Okay, even though the flow is steady and we know the acceleration as a function of change of velocity with respect time is 0, but still here is acceleration, and I will tell you it is not 0. Okay, I will show you here it is not 0. Okay, now when you have this streamline, okay, I told you we have a normal to it, okay, and the tangent gives us the velocity. Okay, now the acceleration, we have two accelerations, okay, acceleration along the streamline and we have acceleration along the normal. Okay, now what is acceleration? Acceleration is this rate of change of velocity, right, dv by dt, right? But since it is steady, it should be 0, but no, it is not. I will show you how. Because since for example this is point 1 and this is point 2, okay, now I told you in a steady flow all the particles at position 1 have same velocity, but the same particles when they enter the position 2, the velocity is v2. Okay, it means the velocity has changed. So because the velocity has changed, right, the velocity has changed from v1 to v2, but not because of time but because of position, right? One is at different one position and the point 2 is another, it is at another position, position 2. So we have a change in velocity along the position, and the change in velocity along the position, because this is the streamline, we will call this position as S along the streamline. Okay, so change in velocity with respect to the position dv by ds is not 0. Okay, and this is the answer of this question, that why do we have a non-zero acceleration? Okay, why is there this factor, although it should be 0 because we have a steady flow? But we will, if someone asks you this question, velocity is dv by dt is 0, how come we have acceleration? You will say the acceleration is because of dv by ds, although the acceleration because of the time is 0, but we do have another kind of acceleration, okay, and which is acceleration with respect to the position, velocity, rate of change of velocity with respect to the position, it is not 0, right? Because acceleration is rate of change of velocity, right? It can be with respect to time or it can be with respect to the position too. So this is 0, but we don't want these zeros. Okay, so we will change it a bit so that it becomes non-zero. Okay, so we can write dv by ds times ds by dt. Okay, now again if you see these ds and ds, right, they will cancel out and we have again dv by dt, right? So it is the same thing. Okay, so I have converted it in delta v by delta t into dv by ds. Okay, how? Multiplied by ds by dt. And how did we do that? We call this as chain rule. Okay, chain rule of differentiation. I don't know if you have heard about this in mathematics, okay, in the calculus now, but the thing is that simply I divide it with the same factor and I multiply it with the same factor. Okay, since they are the same, they will not change. Okay, it is again this and this is the same thing again, but here it is non-zero. Okay, so from here I can write acceleration along the streamline is dv divided by ds times, now ds by dt is what? Rate of change of position with respect to time. Rate of change of position with respect to time is velocity. Okay, so it is v is the velocity. Okay, so here I can write acceleration. I can write here what I can write it as density times, now acceleration along streamline is what it is, rate of change of velocity with respect to the along the the stream times v. Okay, so I will copy it. You should better remember this equation. Okay, so this is our final equation. Okay, so this is our final equation. Okay, you should better remember this. Okay, now this equation is called as equation of motion. Okay, of fluid, rather I will write it as of steady, right, because we have a steady flow, steady, and viscosity is 0, so it is inviscid fluid. Equation of motion of steady and inviscid fluid along a streamline S. Okay, because we denote the streamline with S. Okay, so this is our equation of motion. Okay, now here are some key insights. I can like we have this term delta P by delta S. Now try to understand what it means. Now delta P by delta S, it seems like rate of change of pressure with respect to the path, rate of change of pressure along the streamline, right? So it is we call this as pressure gradient. Okay, but remember we have this negative sign here. Okay, so what does this negative signify? We have this negative here, right? So here the negative means pressure decreases. Okay, pressure decreases along a streamline, right? Okay, then do we have another key insights? We have this delta V by delta S. Delta V by delta S is what? Because delta V by delta S is what? Rate of change of velocity along the streamline, right? And rate of change of velocity with respect to anything is acceleration. But since we are talking about this S streamline, so it is acceleration along streamline. Okay, now because of this we have the velocities. Okay, so if you see a streamline, if a velocity of all the fluid particles entering this position is v1, and here at this position the velocity is v2. Why it is not v1? Here also it is v2. Okay, why? It is because the acceleration, when a body accelerates, its velocity changes. Okay, so on a streamline you will see the velocity is different. Okay, now also the key insight here, because of this delta P by delta S, it means pressure is varying along the streamline. Okay, this delta P by delta S tells us if pressure here is P1, but because it is varying along the streamline, so here the pressure is going to be P2. Here the pressure is not going to be P1 again, because it is varying along the stream line. Okay, these are the key insights. Okay, now delta P by delta S is pressure gradient along streamline S. Okay, now what if we have this streamline? Okay, let us say the streamline is along x-axis. Okay, then delta P, here it is pressure the pressure gradient is delta P by delta S, right, negative. What is going to be the pressure gradient here? It is going to be negative delta P by delta X, okay, because it is along X axis. Here it was along S, so it was delta S. Here it is along X axis, so here it is along, it is X. So if it was along, for example, let us say this one is Y now, okay, in this case the the pressure gradient is going to be minus delta P upon delta Y, okay. So don't get confused if you see a problem, the streamline is along X axis, okay, so you will just replace it, okay. So I think that is, I believe that I have given a very simplified explanation of how we can apply the Newton's second law in fluid dynamics to get our equation of motion, okay. Now I think now I will solve a problem, okay. I will solve a problem here, okay, on this equation of motion, and then we will conclude this lecture, okay. Okay, so here we have this problem, okay. Now in this problem, some fluid is moving from A to B, okay, and at B it is hitting this this ball, okay, and because of this, the velocity is 0 here at point B, right. So it is like this, point A, point B, okay, the fluid is flowing like this, right, along this, and this is X, okay. So the streamline is X, okay, we have the streamline, okay, and here the velocity is V naught, right, velocity at A, and at B the velocity is 0, okay. Now what is the question? The question is we have to find the pressure variation, okay. So how do we find the pressure variation? We are going to use our beautiful equation of motion, okay. So this is our equation of motion, so I will just copy it as it is. Here is our equation. Okay, now here it is horizontal, right. I told you the theta is what? Theta is the angle between the streamline. If this is our streamline S, theta is the angle between horizontal and the streamline. Since we have this horizontal line, the theta is going to be 0, so sine theta is going to be what? 0. So all of this term will cancel, right. Okay, now again we have this velocity given here. We need this, okay, we don't need this one. We need the velocity terms because we have the velocity is provided, okay. So let me rearrange it here. So this is our simplified equation, okay. We have to find the pressure variation, okay, we have to find the P, okay, but we have delta P by delta S. So what we are going to do, I will show you here. We have V is provided, right, V is provided, so from V we will find, but because it is along the X streamline, so it is going to be delta V upon delta X, and delta P upon delta S is going to be delta P upon delta X, okay, remember. So we will find V, okay, we got this V, then we will find we will differentiate V with respect to X, so delta V by delta X, then we will find delta V by delta X, okay, we found this, then we will multiply it with density, right, and then what we get, we will get delta P by delta X, right, we will get delta P by delta X, okay, but we need pressure, right, pressure variation. So but we have delta P by delta X. How we are going to do, we will integrate it, okay, integrate, and we will get pressure variation P, okay. So we have these steps. So let's find each step one by one. Okay, now let's first find v. We have v here. V is what? V naught, right, times 1 plus a cube by x cube. Now we have to find delta v by delta x, right? This term, delta v by delta x, it is going to be v naught multiplied by, now differentiation of 1 is a constant, so it is 0, and a cube is again constant, and then we are going to have a cube will be outside, then we are going to have differentiation of x cube, right, 1 upon x cube, right, 1 upon x cube. Okay, but we can write 1 upon x cube to be x raised power minus 3, right, x raised power minus 3. But remember, differentiation of x raised power n is what? I forgot, n times x raised power n minus 1, right? So here we have to, when we do this delta v by delta x, it is going to be v naught a cube, right? It is going to be x minus 3 times x raised power minus 3 minus 1, right? It is going to be x power minus 4. Okay, so I will write this negative 3 outside, right? Okay, so we have this delta v upon delta x is minus 3. I will, rearranging these terms, minus 3 v naught a cube x power minus 4. Okay, or I will write x4 below. Okay, so this is our delta v by delta x. Okay, now again it is saying us something. What does negative mean? Negative means rate of change of velocity, delta v by delta x, rate of change of velocity with respect to x. Okay, as we move along the x, it is decreasing. Okay, negative means decreasing. Okay, and indeed when we move the velocity, the velocity is, as you can see here, velocity is 0 here and velocity is something here. Okay, so from something v naught to 0, right, to 0, how it is going to happen? It is going to happen only when the velocity is decreasing. Okay, so it means we are doing things right. Okay, anyways, that is not our point of interest. We found delta v by delta x to be this, right? Now we will find delta p by delta x. Okay, so I will erase all of this. So here is our delta v by delta x. So what is going to be the value of, we will find delta p by delta x, right? So negative delta p by delta x is going to be rho times delta v by delta x is this, right? Now this is negative minus 3 v naught a cube divided by x power 4 times v, right? V naught times 1 plus a cube by x cube, right? Now this is rho times, this is v naught and this is v naught, they will multiply with each other. Okay, v naught and v naught, this is v naught square. Then what do we have? This is 3. Now this is minus and this is minus, right? Negative and negative, they will cancel out. Okay, so we have, this is 3 here. Okay, 3 rho v naught square a cube, right, times 1 plus a cube by x cube divided by x power 4. Okay, so we have delta p by delta x. Now we will integrate it, we will get p. Okay, so I will sorry, here it was, negative was already cancelled here, right? Now I will throw this delta x to this side. Okay, so this is our delta p, and we will integrate it. Okay, so integration, because all of these is constant, so integration will begin from here. So integration of delta p is p, then it is 3 rho v naught square a cube times integration of x power minus 4 plus a cube times x power, now 4 plus 3 is 7, x power minus 7 delta x. Okay, now remember, integration of x raised power n is x raised power n plus 1 divided by n plus 1. Okay, so pressure is going to be 3 rho v naught square a cube. Now x raised power minus 4, it is going to be x raised power minus 4 plus 1 is minus 3 divided by minus 3 plus a cube, x raised power minus 7 plus 1 is minus 6 divided by minus 6. Okay, now I can write 6 as 2 times 3. Okay, and minus 3 I will keep it common, minus 3 here. Okay, so they will cancel out here. Okay, now I will distribute the a cube inside, so it is going to be p is 3 rho v naught square, right, but negative, but 3 and 3 will cancel, so it is only this. Then we have, this is a cube. Now x raised power minus 3 is 1 divided by x raised power 3 plus a cube times a cube is a power 6. Now x power minus 6 is x power 6, right? So we have this pressure is negative v naught square times a by x whole cube plus half of a by x power 6. Okay, so this is our pressure variation. Okay, now again we have the pressure variation is negative, it means the pressure is dropping. Okay, and which is indeed true. Okay, because the pressure drops because of all the opposing forces, the friction. Anyways, this is how we found the pressure variation. Okay, and in this problem we have learned how to apply our beautiful equation of motion. Okay, again you should remember this equation, and also you should understand the various key insights of this equation. Okay, so thank you so much for watching my video lecture, and in the next class we will talk about the Bernoulli equation. Okay, so in this class if you have any doubts you can comment or you can contact me. Okay, so see you in the next class. Thank you.